This is your presenter, Asloob Mudassar, and I am presenting slide number 17D of the course on atomic and molecular physics. In the today's lecture, I shall be covering the following topics: measurement of nuclear spin, measurement of nuclear magnetic moment, and measurement of nuclear magnetic resonance. And this is the last lecture of the series on nuclear hyperfine structure. I can be measured from the optical spectra of the hyperfine structure. You see that here in this chapter, when I am talking about hyperfine structure, it means I am talking about nuclear hyperfine structure by taking into account the nuclear spin I and the nuclear magnetic moment mu I. So I can be measured from the optical spectra of the hyperfine structure. Mu I can be measured only in the presence of electronic field, which is Bj at the nucleus. So mu I can be measured only in the presence of the electronic magnetic field Bj at the nucleus. The magnetic field Bj cannot be measured independently of the nuclear spin. So it means that in order to measure Bj, we require nuclear spin to be measured first. Other methods are required to determine mu I, and mu I is the nuclear spin magnetic moment. Mu I can be measured using Stern-Gerlach experiment method, provided the electronic shell of the atom is diamagnetic. Here diamagnetic mean that the total spin, that is the electrons are pairing each other. That is in the shells the electrons are completely paired, which means that the total spin of the electrons in the shells will be equal to 0. So mu I can be measured using the Stern-Gerlach method, provided the electronic shell of the atom is diamagnetic. So you see that here, if the atoms or if the atoms are diamagnetic, it means that we can measure mu I using the Stern-Gerlach method. Otherwise, deflection of the beam due to the nucleus will completely obscure the 1000-fold greater effect of the electron shell moment. So you see that if the material or if the atoms don't belong to the diamagnetic material, then you see that we cannot measure mu I because the splitting or the deflection of the beam due to the nucleus will be completely obscured by the 1000-fold greater effect of the electron shell moment. So the electron magnetic moment will be 1000 times greater than that of the magnetic moment due to nuclear spin, and so the nuclear spin will be and so the deflection of the beam due to the nucleus will be completely obscured by the 1000-fold greater effect of the electron shell moment. So in the presence of the spin of the electron moment, the nuclear spin mu I cannot be measured. So it means that mu I can only be measured in the presence of the diamagnetic materials. In 1933, Stern, Fritsch, Esterman measured mu T, that is the magnetic moment of the proton for hydrogen molecules using the method given earlier. In their method, H2 traveled. You see that I have also talked about a little bit method of this one in the previous lecture. In their method, hydrogen molecules traveled a path of 150 centimeter and a deflection of 10 to the power minus 20 millimeter. The inhomogeneity of the field was 800 Tesla per meter. The measurement of the proton magnetic moment was not precise. So you see that in this method, the molecules, the hydrogen molecules were used. They traveled a distance of 150 centimeter, and they underwent a magnet deflection of 10 to the power minus 2 millimeter. The inhomogeneity of the field was 800 Tesla per meter, and the measurement of mu p was not precise. In 1937, Rabi used atomic or molecular beam resonance method, a more precise method. You know that we have discussed the electronic resonance method in one of the previous lectures. Here we shall be talking about the nuclear resonance method. So in 1937, Rabi used atomic or molecular beam resonance method, a more precise method. The method measured the Larmor frequency of the nuclear spin in an external magnetic field, similar to the electron spin resonance. So you see that this method involves the nuclear spin resonance nuclear spin Larmor frequency. And if you could measure the Larmor frequency of the nuclear spin in the presence of the external magnetic field, which is very similar to the case when we discussed the electron spin resonance, then you see that measuring the Larmor frequency, we would be able to measure the nuclear magnetic resonance, or we can also measure the mu p, that is the magnetic moment of the protons, can be measured very precisely. Either we measure mu p, or we can measure the ratio mu I over I, where mu I is the magnetic moment of the nuclear spin and I is the nuclear spin quantum number. So the ratio of this one can also be determined in those experiments. The method requires that the field due to electronic shell Bj must vanish at the nucleus. So you see that this method in which we have discussed that we need to measure the Larmor frequency of the nuclear spin, or we can measure the ratio from mu I to I. It would require that the Bj, that is the electronic, that the field due to electronic shells, must vanish at the nucleus. There are some atoms, for example, mercury, copper, carbon, sulfur, and molecules, for example, H2O, CaO, lithium chloride, NH3, for which the magnetic moments of the electronic shells add up to zero. So these are the atoms: mercury, copper, carbon, sulfur. These are the atoms for which the magnetic moment of the electronic shells at the nucleus add up to zero. And there are some molecules, for example, H2O, CaO, lithium chloride, and NH3. These are the molecules for which the magnetic moment of the electronic shells at the nucleus add up to zero. So it means that for these atoms and molecules, we can use the method as described by Rabi in 1937, and we can measure the Larmor frequency of the nuclear spin, and we can also calculate the ratio of mu I to I. Because in all these measurements, the Bj at the nuclear site is zero. Now you see that let's calculate the magnetic potential energy in the presence of the nuclear spin and in the presence of the applied magnetic field B naught. So B naught is the external magnetic field and mu I is the magnetic moment of the nuclear spin. So we have V is equal to minus the dot product of mu I and B naught. If you expand this dot product and substitute the value of mu I, which I have shown in green, then of course the equation becomes minus gi into the square root of I into I plus 1 times mu n, and then we have B naught and the cos of the angle between I and B naught. So we can separate out some terms, and the rest of terms I have gathered them in the parenthesis, which is the square root of I into I plus 1 multiplied by the cos of the angle between I and B naught. The term in the red can be replaced by Mi, where Mi is the magnetic quantum number of the nuclear spin represented by Mi. So this whole term has been replaced by Mi. And this is what I have discussed in one of the previous lectures of this series. So we have magnetic potential energy V, due to the nuclear spin in the presence of the applied in the presence of the external magnetic field equal to Gi, which is the G factor of the nuclear spin, mu n, which is the nuclear magneton, B naught is the external magnetic field, and Mi is the magnetic quantum number due to the nuclear spin. The energy difference delta E between two neighboring orientations in the presence of a B naught, that is when delta Mi is equal to plus minus 1 is given by. So you see that you have this potential energy which depends upon the value of Mi, and if you want to write down the energy difference between two neighboring levels in the hyperfine structure, then you can replace Mi by delta Mi is equal to plus minus 1, which indicates that we are considering two neighboring levels in the hyperfine structure, and the energy difference between those levels delta E will be equal to delta E is equal to Gi into mu n into B naught, because we have set the value of delta Mi is equal to plus minus 1 for the neighboring for the two consecutive hyperfine structure levels. Let the sample is irradiated with a frequency nu such that, now you see that this is a delta E which is known to us, that is this is the separation between two hyperfine levels, hyperfine nuclear levels or nuclear hyperfine levels. So the difference of energy between two such levels is given by equation number 40. And if we illuminate such a material or irradiate such a material with a frequency nu, then we can have such that the nu is chosen in such a way that the quantum energy of the incident light h nu is equal to delta E. That is, the quantum energy of the incident light is equal to the energy gap between the two consecutive hyperfine levels. Here you can solve the value of E and you can get this result. Multiplying both sides by 2 pi on both sides, we get this relationship, and 2 pi nu can be replaced by omega L. So omega L is equal to Gi into mu n divided by h bar, and then we have V naught. And you know that this term Gi mu n over h bar is actually a gyromagnetic ratio gamma, which is more precisely referred to as the nuclear gyromagnetic ratio. You know that omega L depends upon the product of two quantities, the gyromagnetic ratio of the nucleus and the applied magnetic field B naught. And this is the Larmor frequency of the nucleus. So this is the Larmor frequency of the nucleus in the presence of the magnetic field B naught. Omega L can induce transitions with delta ML is equal to 0 plus minus 1. So you see that here when we are illuminating the sample with a frequency nu, to which the gyromagnetic to which the Larmor frequency omega L is given by equation number 41, then such a frequency nu of the incident beam can induce transitions in the material with the quantum numbers delta ML is equal to plus minus 1. And the nuclear spin changes in orientation. That is, the nuclear spin, for example, if there is an absorption between the two levels of the hyperfine structure, then between these two levels the nuclear spin will change. And if there is absorption, the nuclear spin will change, and if there is an emission between those two hyperfine levels, then the nuclear spin will also change. So there is a change of nuclear spin due to the transition following the optical rule, that is delta Mi is equal to plus minus 1. So when the optical transitions obey this rule, delta Mi is equal to plus minus 1, then of course the nuclear spin I will change both in absorption and in emission. So such an this is called the Such a resolution is called the electron spin nuclear spin resonance, because in the nuclear spin resonance the spin will change either in absorption or in emission. So the nuclear spin I will change its sign, that is, will change its orientation, will change its direction. So under that condition, it is referred to as the nuclear spin resonance. Resonance means that between these two levels, the emission and the absorption will take place at the same level. That is why it is called a resonance level. And it is called a nuclear spin resonance method, because the nuclear spin will change its orientation either in absorption or in emission. The frequency nu of the incident beam, which causes the nuclear spin resonance, is given by this relationship: nu is equal to gi into mu n over h bar into b naught. So you see that here you make a correction, it is not h but it is h bar. This quantity is h bar. So I have introduced I in the numerator shown in red and in the denominator shown in red. And I have also introduced a quantity mu I, which is the nuclear magnetic moment, in the denominator as well as in the numerator, represented in blue. And here this is not h bar, this is h bar. So if you plug in the values of all these quantities, it becomes equal to 762.3, and then I have mu I over I into V naught. So you see that our incident frequency, if matches with the quantities on the right hand side as shown in equation number 42, then of course the nuclear spin resonance will occur. So the nu is a known quantity. V naught, which is the applied external magnetic field, is also a known quantity. So mu I over I, that is the ratio of the nuclear spin magnetic moment to the nuclear spin, can be calculated. So mu I over I can be calculated as shown in equation number 42. Resonance is detected by the deflection of atoms or molecules in inhomogeneous magnetic field. And this is what we shall discuss in detail using an experimental setup. Resonance is detected by the deflection of atomic or molecules or molecular beams when passing in inhomogeneous magnetic fields. In the absence of a B1, so there is an magnetic field B1, the three magnets A, B, C are adjusted such that the particle beam is received at the detector D. Now you see that you will ask the question, what is B1? Because so far I have been talking about B naught, which is the applied external magnetic field. Now I am going to talk also about the magnetic field B naught. And for that one, I am talking about three magnets A, B, and C, and also a detector D, which will receive the particle beams. So let me first of all discuss the experimental setup in briefly. This is the slit through which the atomic beam or the molecular beam will pass. Here I am talking about the atomic beam. The atomic beam will pass. If there are no magnets A, B, C are the magnets, if these magnets are not present, the beam will travel through the dotted path, will pass through another slit and will reach at the detector D. But when you apply the magnetic fields through the magnets A, B, and C, A, B magnets provide inhomogeneous magnetic field, whereas the magnet C provides a homogeneous magnetic field. And A and B magnets are oriented in such a way that the inhomogeneous magnetic field produced by the combinations of magnet A will be cancelled out by the combination of magnets B. And you know that C is a magnet which will provide a homogeneous magnetic field. A and B will provide inhomogeneous magnetic field in opposite directions, and C will provide a homogeneous magnetic field. And you know that this is what the nuclear spin has been shown, that how it will behave I have shown this with an arrow over here, because it will precess the nuclear spin will carry out its precessional motion about the magnetic field over here, and it will carry out a magnetic field in the downward direction over here as shown. And you know that I have shown the change of a magnetic field with the distance z in the downward arrow over here and in the upward arrow for the magnet B. Because the z direction is perpendicular to the direction of the dotted line shown. The z direction is perpendicular to this, either in the upward direction or in the downward direction. This would not matter. And here you can consider the magnetic field B as the magnetic field B naught. So curly B naught over curly Z for due to the magnet A, and also curly B over curly Z due to the magnet B. And you know that their directions are shown that they are oppositely directed, having the same magnitudes. And you know that there is a slit S placed at the center of the magnet C. And there is a homogeneous magnetic field in this region of the magnet C. So when there is a deflection, you see that there are two paths shown, because the beam will be deflected in the two paths. Then the beam will pass through another slit placed at the center of the magnet C, where it will be unaffected, and then it will enter in another inhomogeneous region due to the magnet B, and it will again be combined and will reach the detector D. So the detector will record the current. Now you see that I am going to apply the magnetic field B1 over here. B1 is a magnetic field which is perpendicular to the magnetic field due to the homogeneous magnetic field C. And B1, what the B1 will do, you know that the homogeneous magnetic field due to the magnet C and the magnetic field due to magnetic field which is perpendicular to the homogeneous magnetic field due to C. These two magnetic fields will provide the resonance resonance frequency, and will provide the magnetic field such that the resonance will occur between the two levels of the nuclear hyperfine structure. When the magnetic field due to magnets C is increased in strength, then the separation between the hyperfine levels will increase. So the constant magnetic field C will, if you increase the value of the constant magnetic field C, which is the homogeneous magnetic field, then the separation between the hyperfine levels will increase. And if you decrease the magnetic field due to magnet C, then of course the separation or the splitting between the hyperfine levels will decrease. So the separation between the hyperfine levels will be controlled by the homogeneous magnetic field due to the magnets C. So when you fix the value of magnets C, then of course you fix the separation between the two levels of the hyperfine splitting. And B1 is the magnetic field which will energize the absorption from the lower hyperfine level to the upper hyperfine level. And similarly, the magnetic field due to B1 will also induce the will also induce the transition from the upper hyperfine level to the ground hyperfine level to the lower hyperfine level. So B1 will control the transition between the levels. B1 will provide adequate energy that will match with the energy difference between the two hyperfine levels, and then the transitions, either absorption or the emission, will take place. That is, the nuclear resonance will be energized by the magnetic field B1. Now there are two options. Either you fix the value of the magnetic field due to the magnets C, and then you vary B1 from the initial stage unless it matches the energy, the energy due to the magnetic field B1 matches with the energy separation between the hyperfine levels. Then of course the transition will take place from the lower hyperfine level to the upper hyperfine level, and also from the upper hyperfine level to the lower hyperfine level. That is, the resonance will occur, which we call here as the nuclear resonance. Due to this resonance, that is absorption to emission, then emission to absorption, then absorption to emission, and then emission to absorption. This process will continue due to the resonance process. But a small population difference will appear in the population of the two levels. In principle, the emission from the upper to the lower, and then absorption from the lower level to the upper hyperfine level, then emission, then absorption, then emission, then absorption. This process will continue. And in principle, the population of the two levels will be the same. But in practice, we found that there is a small difference between the populations of the two levels. And that small difference will absorb the energy, and due to that one, there would be a change in the structure of the beams, and of course the beams will be deflected away from the detector, and the detector will measure a change in current, or a dip in current will be measured by the detector when the resonance will occur. So whenever the resonance will occur, these beams will not reach the detector, or a part of them will not reach the detector. So the detector will record will record a fall in current, and of course a dip in current will be observed. And this will only happen when there is a resonance condition met. The second way of meeting the resonance condition is that you fix the value of a B1, some arbitrary value, for example, fix the value of a B1 and change the value of and keep on changing the value of the homogeneous magnetic field due to magnets C. Since you are keep on changing the value of the constant magnets C, it means that you keep on changing the separation of between the two hyperfine levels. That is, you are changing the delta E between two hyperfine levels, and ultimately a stage will reach when the separation that which you are controlling by controlling the magnetic field due to the magnets C. That magnetic field will change the separation, and that separation will match with the magnetic field, will match with the fixed magnetic field B1, and then again the resonance condition will occur. So now I am going through very quickly the text, because I have explained in much greater detail the setup. In this case, the deflection due to magnet A is compensated by the deflection due to magnet B. The magnets A and B provide inhomogeneous magnetic field. The magnet C provides homogeneous magnetic field. A high frequency field B1 is applied perpendicular to B0, which is due to the magnet C. Atomic beam resonance according to Rabi is shown. And you know that I have explained this condition, that B0, magnetic field B0 due to the magnet C will change the separation between, will control the separation between the hyperfine levels, and B1 will provide an energy that the resonance between the two hyperfine levels will occur when the energy due to the field B1 matches with the energy gap between the two hyperfine levels, and the resonance will occur, and due to resonance there would be a fall in the detector current, and a dip in current is recorded at the resonance condition met. The resonance field B1 will cause some nuclei to flip from one orientation to another. So you see that in the nuclear spin resonance method, which is the resonance method I have explained just, there will be an absorption from the lower hyperfine level to the upper hyperfine level, and similarly there will be a transition from the upper hyperfine level to the lower hyperfine level. And in these two transitions, either in absorption and in the emission, the nuclear spin will flip. The displacement in the field of magnet B is no longer symmetric to that in the field of magnet A. Due to this flipping, the affected particles will not reach the detector D. Current I is measured as a function of the frequency nu of the magnetic field B1. So this is the one condition. But if you set B1 to be constant, then I, that is the current, is measured as a function of the strength of the magnetic field B naught due to magnet C. When the resonance condition is again satisfied, when you change the value of the magnetic field B naught due to the change in the values of the magnets C, the current I will be minimum. That is, a dip in the current will be observed at the resonance condition. The plot of the current I at the detector D is shown on the next page. So let me show you first this plot. That is, the dip in current is recorded at the resonance. You know that this is the intensity of the beam reaching at the detector, and this is the B naught. Here you have fixed the value of a B1 to be equal to 7.76 megahertz is the value of a B1. This is the magnitude of the B1 magnetic field. And here you are changing the magnetic field due to B naught. And the values are given in Gauss, which changes from 1900 Gauss to 2050 Gauss. And B naught is changed by changing the values of the magnet C. So when you change the values of the magnet C, keep on changing, the current is constant. At some time you will see that there will be the current starts falling downward. At the detector, the current will decrease. So this is the condition that we are approaching the resonance condition. So at this value of the magnetic field B, which is slightly below the value of 1950 Gauss, a nuclear resonance condition will occur. And a complete dip, that is the minimum value of current, will be recorded at the detector. So if you increase the value of a B naught further, then of course the resonance condition will slightly be disobeyed, and then you know that it will be completely disobeyed at a value around 2000 Gauss. So you see that the intensity at the detector will decrease at the resonance condition. And here I have drawn this diagram saying that the value of the B1, which is equal to 7.76 megahertz, is fixed, and we are changing the value of a B naught. Data curve for the Rabi atomic beam resonance experiment for the fluorine nuclei. So you see that the curve I have shown you is just for the fluorine nuclei, as shown on the next page. The intensity of the at the detector D is at a minimum for B1 is equal to constant when the homogeneous magnetic field B naught due to the magnet C fulfills the resonance condition. To calculate mu I, that is the spin magnetic moment, that is the magnetic moment due to nuclear spin. The nuclear spin I is first measured from the hyperfine levels in the optical spectra. So you see that you can calculate the hyperfine levels, and then from these hyperfine levels through the optical spectra, you can determine the value of the nuclear spin I. The Rabi atomic or molecular beam resonance method permits the measurement of this ratio, that is the ratio of omega E to omega P. And this omega is the omega corresponding to the resonance frequency. And the E means that it is the omega resonance is the resonance frequency for the electron, to its ratio for the resonance frequency of the proton or the nuclei. So the ratio of this one, that is omega resonance of electron to the omega resonance of a proton, can be measured to a great precision. That is, the Rabi atomic or molecular beam resonance method permits the measurement of this ratio, that is the omega resonance due to electron and its ratio to the omega resonance due to proton, to a great precision. Exact value of a B naught is not required in these measurements. Omega resonance E to omega resonance P is measured by letting particles with pure electron spin properties pass through the same apparatus as the molecular beam with pure nuclear spin properties. So you see that omega resonance E will be measured when the particles with pure electron spin is used. That is, the orbital part of the electronic beams is not present, only the spin part of the electronic system is present. And similarly, omega resonance P can be measured when the molecular beam with a pure nuclear spin properties are present. So omega resonance E due to particles with pure electron spin properties, and omega resonance P due to particles with due to particles with pure nuclear spin properties. These two factors can be determined very easily with these two beams: pure electron spin beams and the molecular beams with pure nuclear spin. So the ratio of mu E to mu P is equal to GE into mu B over GP into mu N. So this can be determined, that is, this ratio can be determined because G is known very precisely from some other experiments. And one of such experiments is what we have discussed while we discussing the simple hyperfine structure in one of the previous lectures. So G is known very precisely from some other experiments. GP is measured and mu P is calculated precisely. So you see that we can measure the value of Gp, mu B and mu N are also known precisely, and mu E, you know, that is determined because G is known. So mu P is calculated precisely. For protons, Rabi obtained this relationship, that is the nuclear magnetic moment is equal to, within the parenthesis we have 2.875 plus minus 0.02, and then it is multiplied by mu N, where mu N is the nuclear magneton. So equation number 44 provides you a secondary standard. So this can be used as a secondary standard for other nuclei or for exact measurements of a B naught. So we can use equation number 44 for other nuclei as a secondary standard, or we can use this equation in order to measure the value of a B naught. Purcell Bloch in 1946 established both theoretically and experimentally that the precessional motion of nuclear spin is largely independent of the translational and rotational motion of the nucleus. So you see that this was very profound findings of the Purcell and Bloch, that the nuclear spin is largely independent of the translational and rotational motion of the nucleus. The nuclear spin resonance can be applied not only to the free atoms but to the atomic nuclei in liquids and solids. So you see that nuclear spin resonance method can be studied for the free electrons and also for the atomic nuclei in liquids and solids. The principle of nuclear magnetic resonance in condensed phase, that is in the materials in which the molecules or in which the atoms are completely solidly packed, is explained. B naught is fixed. Radio frequency B1 is produced by varying the frequency of the generator. So let me show you the experimental setup also over here. This setup. So here is the signal generator, and here is the radio frequency bridge in which we change the frequency of B1. So B1 frequency is changed over here, and this is the receiver which contains power meter, and this will record if there is a change in the magnetic field B1 due to resonance. So when the resonance will occur, the receiver containing power meter will record the measurement. So N and S are due to the permanent magnet, or their magnetic field can also be changed using the sawtooth wave generator. So sawtooth wave generator can also be used to change the value of the magnetic field B naught, and the value of a magnetic field V1 is changed by the radio frequency bridge circuit. And you know that this is a sample which contains the material, and there is a coiling of this frequency signal around the sample contained in this glass tube. And of course, a magnetic field B1 is produced across the sample. So when the value of the magnetic field V1 matches with the separation of the hyperfine levels in the material, then of course the resonance condition will occur. That is, the energy from the field will be absorbed by the sample, and that reduction in the value of the field of the magnetic field will be recorded through the receiver through this radio frequency bridge circuit. So the receiver which consists of the power meter will record the change in the change in current through the sample values, and then the signal can be displayed on the oscilloscope shown over here. This is sawtooth wave generator signal which is fed to these two permanent magnets. For example, B naught magnets will also be displayed. This signal will also be displayed on the scope, so that we can know the value of the strength of the magnetic field B naught. So you see that after having explained this circuit, I am now going through the paragraphs very quickly. The principle of the nuclear magnetic resonance in condensed phase is explained. B naught is fixed through radio frequency field B1. Radio frequency field B1 is produced by varying the frequency of the generator. At resonance, the frequency of a B1 matches with the nuclear alarm frequency, nuclear alarm precession frequency. The sample absorbs energy from the field B1. A power meter used as a receiver indicates this energy absorption. That is, the power meter contained at the receiver end will record this energy fall. So a power meter used as a receiver indicates this energy absorption from the field B1. The resonance may also be detected by observing a resonance signal induced in a second coil, placed perpendicularly to the first one. So you see that here we have used the power meter as a receiver that would indicate the absorption of energy by the sample from the field B1. But the second option is that you can use another coil close to the sample with this existing coil, but may be oriented opposite in polarity, opposite in direction. Then you see that when the field is absorbed by the sample, then due to the induction process, the other coil which is placed close to the coil wound around the sample, that coil will be induced with some change in magnetic field, and then of course the resonance condition can also be measured. So the resonance may also be detected by observing a resonance signal induced in a second coil placed perpendicular to the first coil. B1 of the fixed frequency is used, and B0 is varied in order to sweep through the resonance. So you see that in this case, you can keep the value of B1 fixed and you can change the value of B naught. And the value of B naught can be changed by using the sawtooth wave generator. So for proton with GI is equal to 5.58 and B naught is equal to 1 Tesla gives you the frequency which is equal to 42.576 megahertz. This is the resonance frequency of the sample, and the sample that we are discussing is actually the fullerene nuclei. This is the fullerene nuclei is the sample. And for these fullerene nuclei, we have the value of GI which is equal to 5.58 and the magnetic field that we are applying is B naught is equal to 1 Tesla. And the resonance frequency that we have measured is 42.576 megahertz. And you know that the quantum frequency corresponding to this frequency delta E, which is the separation between the hyperfine levels, is equal to h nu is equal to 1.8 into 10 to the power minus 7 electron volt. So this is the quantum energy difference between the two hyperfine consecutive levels. So I have explained this setup, So let me read the corresponding paragraph. Simple nuclear spin resonance apparatus. The sample is placed in a simple gas tube between the poles of a homogeneous magnet, providing the magnetic field B naught. High frequency B1 field is applied across a bridge using an induction coil. For better detection of the resonance, the field B naught can, can also be modulated by an additional coil which is placed over here and is also shown in the experimental setup. An additional coil shown indicated as a modulation coil and controlled by the sawtooth wave generator. Due to this small energy splitting, the Zeeman levels of the nuclear spin system are equally populated. According to the Boltzmann distribution at room temperature in thermal equilibrium, the population of both the Zeeman levels in the nuclear spin should be the same. Here you see that I am talking about the Zeeman levels because I am using the magnetic field which is small in strength. So if you increase the same magnetic field in the same setup, then you know that these will be called as the hyperfine levels of the nuclear spin. So you see that in this case, if you consider small magnetic field, then of course you may be referring to the Zeeman levels of the nuclear spin. And these two levels of the Zeeman levels of the nuclear spin must be equally populated because of the Boltzmann distribution at room temperature in thermal equilibrium. Thus, in resonance, the same number of absorption and emission transitions are induced and only a small net effect remains. So this point is very important that only a small net effect remains. That is, there will be a small separation, small difference between the populations of the two levels of the upper level with respect to the lower level. That is, there would be a small population between the Zeeman levels or the hyperfine levels. At the room temperature, the population difference between two nuclear Zeeman levels or the hyperfine levels in a field of 1 Tesla is about 10 to the power minus 6 of the populations present in these two levels. So you see that a small fraction of that one may avoid the equivalence between the population of the two levels. This is a very small difference. The extremely small population difference is responsible for the nuclear resonance signal. So you see that this signal, which is very small, is responsible for the nuclear resonance signal to be measured. Because this signal will be responsible to generate a dip in the current measured at the detector. For high sensitivity, stronger magnetic fields of the order of 12 Tesla using superconducting coils giving you a frequency nu of 500 megahertz for a proton spin can be applied. So if you apply much stronger magnetic field, the separation between the levels will be much greater, and then of course a very high frequency, for example, of the order of 500 megahertz is required to cause a resonance between the levels. Relaxation process re-establish the population differences. You know that the relaxation process is continued, that is the population from the upper laser level will be continually falling to the lower level, lower hyperfine level, and then from the lower hyperfine level again the absorption will take place. So a relaxation process will keep on occurring, will keep on trying to equalize the difference in population between the two levels. Otherwise, the resonance would quickly become saturated. That is, the levels would all be equally populated, and no further signal would be observable. So it means that a relaxation process is required so that there will be a small difference of a population should always be present between the two Zeeman levels or between the two hyperfine levels, depending upon the magnitude of the applied magnetic field. And then otherwise, if the population becomes exactly equal, then the levels would be equally populated and no further signals would be observable. In nuclear magnetic resonance spectrometers, stationary or continuum wave methods are not used. So you see that in nuclear magnetic resonance spectrometers, we don't use the stationary or the continuum wave methods, but instead we use the pulse methods. That is, a pulse is given to the sample. In these methods, one observes the time evolution of the nuclear magnetization I of t. So you see that we provide a pulse to the material, and then we observe the time evolution of the nuclear magnetization I of t following a short, intense, high frequency pulse, and the frequency dependence of the magnetization, which can be I of omega, can be obtained from I of t. From the observed temporal behavior can be calculated. So I of omega can be calculated from I of t using this relationship shown in equation number 45, that I of omega is actually the Fourier transform of I of t. And you know that on the right hand side, I have the Fourier transform integral. So I have I of omega is equal to 1 over 2 pi integral from minus infinity to plus infinity of I of t multiplied by e to the power minus iota omega t into dt. So if you take the Fourier transform of the I of t, which is the temporal quantity, you can find out the frequency dependent quantity. So the time evolution of the nuclear magnetization I of t following a short, intense, high frequency pulse and the frequency dependence of the magnetization I of omega from the observed temporal behavior can be calculated. And you know that I have given you I have explained the integral which can be used to convert the I of t into I of omega. So this is illustrated for a simple case. After a 90-degree pulse, which turns the magnetization away from the z direction and into the xy plane, the y component of the magnetization exhibits an exponential decay with the time constant t2. So you can see this is the pulse that we have applied, and the pulse is you know that is at an angle of pi by 2, that is at an angle of pi by 2 with respect to z axis. So it could be along the x axis or along the y axis. So suppose that if it is along the y axis, then you know that the magnetization along the y axis is given by the curve which is shown in the middle. So this is I of t, that is the time evolution of the magnetization of the sample, and my stands for the magnetization of the sample along the y direction, And you know that after the pulse is given, then the signal will be decaying constantly. So this will be a exponential decay of the signal through sinusoidal way, and the decay rate is given by e to the power minus t over t2, where t2 is given by 2 pi over omega naught, and omega naught is the resonance frequency of the sample. And you know that if you have I of t as shown in the middle, as shown in the curve in the middle, you can find out I of omega. And I of omega is simply shown over here. This is a small pulse having a width, full width half maximum equal to 2 over t2, and centered at a central frequency omega naught, that is centered at the resonance frequency. So at the resonance frequency, we have the frequency omega naught, and on either side of that one, the frequency will deviate from the resonance frequency omega naught. So I of omega is the nuclear resonance spectrum. If several inequivalent types of nuclei are present in the sample, the time evolution I of t becomes more complex. The relevant plot is shown on the next page. That is this plot which I have already explained. So you see that this was the last lecture of the series on nuclear hyperfine structure. So this is the end of this lecture.